it's my pleasure to announce the second speaker of this first afternoon session, Professor Uwe Kähler. Are you ready?
Yep. Let me just share my screen. I think I use this guy. Can you see it?
Yes.
Okay.
So maybe I introduce your talk. So Professor Kähler from the University of Aveiro in Portugal will talk about Quaternionic Volterra operators and triangular representations. Please.
Yes, thank you. Let me only say that my background is actually rather in function theories over non-commutative structures, and that will also be visible here. The talk itself is, well, you will see that one in a minute, is really about specifically quaternionic and also Clifford-algebra-valued operators and functions. And well, since that didn't come up so much right now here, let me actually just give a short motivation for why one actually is considering that one. The original motivation actually goes back to Birkhoff and von Neumann, which initiated something which was called, and still is called, quaternionic quantum mechanics. So not only complex, but quaternionic level. This has been developed since that time, but it never came that much to the forefront, mainly because there are a lot of things you can do in the complex quantum mechanics, which in quaternionic gets rather difficult. So it was interesting and a lot of persons did, but never really to the forefront like the standard one. But basically behind that one is a bigger issue, which actually came back in the last decades, and that's the connection with geometry. Because basically whenever you use rotations, you're actually working with spin groups. So, and applications involving spinners you find in a lot of places. There's one point that in general persons don't like so much to work with spin groups itself or spinor valued functions, so functions taking values in the spin group, but rather you prefer to take the quaternions or a Clifford algebra as values. It's much easier to work in an entire Clifford algebra than restricting yourself to the spin group or the spinor valued. So one of the most well recent ones which are actually coming are the so-called phase representations. The simplest one you actually had a couple of times in the background here. For instance, if you know classic signal processing before 1980, before wavelets, the biggest thing was usually taking the analytic signal. You take your signal, real valued, you take the Hilbert transform, and both together give you the analytic signal, which you then can study the phase and the amplitude and so on, but principally the phase. And these ones are basically just boundary values of holomorphic functions. So the analytic signal is basically just boundary values of holomorphic functions. And of course, one would like to do that one also in higher dimensions. And usually the most simple way of getting phase representations is you take your real valued signal and you take the Riesz transforms. If you put them both together, you basically can show that these are indeed, if you take them even as vector valued functions, but if you consider them as spinor valued functions, you can immediately say, okay, these are boundary values of a type of analytic functions, which is usually called monogenic functions. Well, basically goes back to Stein and Weiss and the Diffraud system and so on, even if it's vague. So that's why I'm actually also pointing out that has been used quite a lot, but also directly spin groups in robotics, computer graphics, and so on. I don't want to go into any of these applications, just want to mention them. Another point, which I also would like to mention, is actually from tomography, especially if you go for diffraction tomography. There you have the point that what you're integrating are not straight lines, but rather, for instance, in diffractions is geodesics in spin groups. Like for instance, the simplest one, if you basically just send X-rays into a sample and you just measure the diffraction, usually what you have is basically your signal goes in, is on S2. What comes out, you measure on the whole sphere, so it's also an S2. And if you look at the rotations which send one ray into another, it's always a great circle on the tree sphere or the pure quaternions, if you want. Another thing from the pure mathematical point of view, you will see is actually, it's especially the quaternionic case is also a toy model for if you want to look how things happen in non-commutative structures. And that a lot of times actually helps. I will simply show a couple of times, even to question standard concepts you have in mind even such simple things like linear algebra and so on, what really is essential and what is not. Okay, let me actually point out just this slide. I mean, everybody probably knows that one. I just mentioned for the notation. Basically, we will not really need the multiplication. The only thing we will need is the conjugation, and the conjugation is basically linked to the norm. More important for us is any rotation or is given as an action on the tree on the, for instance, here in the case of quaternions, action of quaternion or an action of the spin tree on a vector, and that's basically u and u inverse from both sides. There's one important thing here. You have to be careful of quaternions in difference to, for instance, nilpotent groups. If you write down the exponential, the product, the exponentials with quaternions, you will see that the Hausdorff-Berkeley-Campbell formula is not cutting off. So if you take commutators of commutators, there's no commutator which disappears. It's not nilpotent, but rather it's periodic. So if you write it down, you will basically have, after a certain moment, the commutators will go back to things that you have a kind of periodic structure, not a nilpotent structure. And that has effects. Just to give you something, I thought I make it first relatively simple, and just to get you an idea what in spectral theory you actually encounter for problems, just let's look at the problem of Quaternionic Clifford-valued matrices. The first one you will actually see is, obviously there are two types of eigenvalues. You can take the eigenvalue from the left and from the right. But while you find a lot of things, for instance, for eigenvalues from the left, you will actually realize that, first of all, left eigenvalues is a kind of chaos. There's no real nice theory about that one. And there's a reason for that one, because it's actually, when you look from the linear algebra point of view, left eigenvalues are actually useless. You just have take a matrix, make a couple, as an exercise, make just one or two steps with the Gauss algorithm, and you will see that the only eigenvalues which interest you are the ones on the right. And then on the left, they never appear. So that basically means that we are interested only in right eigenvalues. These ones are the ones which interest us, the other ones not. And the next thing is basically kind of trivial calculation. You just can basically multiply with one element from the spin group on the right hand side, you plug it in here and you immediately get this one. And this one is basically a rotation of your eigenvalue. With other words, you have eigenvalues which are actually forming spheres. So strictly speaking, when you want the theory, you're actually having something which is spheres of eigenvalues or equivalence classes of eigenvalues in some sense. The additional thing you have is that the right eigenvalue problem is also nonlinear. That's obvious here. You cannot simply take out constants from the left or from the right. That's one of the big problems. You actually come out of that one. Eigenvalues are spheres, but it also has an effect that you actually can ask yourself simply what happens actually with the standard definitions you actually know. Because this case, since you have lack of commutativity, you can, for instance, ask yourself, okay, standard concepts you know from linear algebra, how good they are actually and how is that? For instance, just to give you an example, I put here the definition, the question of a determinant. If you go to Quaternionic Clifford-algebra matrices, the first things you will see is actually that all these standard definitions via permutations or other things are actually useless. They don't work there. And the reason is basically that the underlying concept, what you want to have for the invertibility, is not exactly the determinant by itself, but rather actually what's underlying linear algebra is a Schur complement. And the Schur complement always gives you a determinant, so you can always use a Schur complement and iteratively define your determinant. This is then what Gelfand called quasi-determinants, but it basically tells you that certain concepts are more fundamental than others, even when in standard linear algebra you don't see that. And that's basically having, and these kind of things having an effect if you want to go for spectra or spectrums, because you can actually see the following. That what happens if you want to do spectral theory for quaternionic operators. Of course, the direct approach would be just you go for the resolvent with where m lambda here denotes multiplication from the right. That's possible, but not that useful. I mean, that's basically what persons already tried since basically right from the beginning. but it runs into a couple of problems. First of all, we already know that thing is a nonlinear operator. So you don't actually have linearity. You actually would have to work with a linear operator. The second problem is a little bit more hidden, but it's also relatively easy to see. If you take the geometric series with T as an operator and your spectral parameter on the other side, that's not the standard one, or let's say I put here just lambda I instead of m lambda. Doesn't matter. Both are not really working. The main problem is basically you cannot get it so easily here, because when you make the geometric series with these ones, you can basically get them interchanged. T lambda minus 1, T lambda minus 1, T lambda minus 1. And that means you have a problem. If you want any kind of analyticity involved, any kind of function theory involved, that doesn't work, because you would like to have something of that type and not T and lambda intertwined where you can't work. So as long as you are happy with a simple spectral theory and let's say L infinity functional calculus or something like this, you can do that one, you can work in that way, but it doesn't really help if you want to have more sophisticated, especially if you want to have functional, function theoretical things. That also has this effect. So I just mentioned, for instance, if you look for this classic spectral theorem for normal operators, that goes back to Teichmüller in 1936. And if you read his paper, actually it was his PhD thesis, there's no notion of a spectrum. He doesn't need it. And he really avoids it simply because it's not actually easy. And there are a lot of things in between. As a way out, there's recently in 2006 appearing the notion of an S spectrum. And the basic idea behind that one is actually not that difficult, but rather unusual, in the sense that you actually use a trick. Usually you do when you actually are used to work with Dirac operators. I mean, there are a lot of things where Dirac operators, if you study them directly, a little bit more difficult, but you can always imagine that the Dirac operator factorizes a Laplacian. So if you take the standard Dirac operators over n, you square them up, it's minus a Laplacian. So it's actually a square is a positive definite scalar operator. So, and you can move a lot of things over that one. And that's basically the idea behind this one. If you make extremely simple calculation, you just multiply that one, then as long as you can commute S and Q, you would get this term here. But this part here, the last term, that actually is independent of Q and S commuting. So if I put here another A in front, as long as Q basically can multiply and take out from both sides. So this one actually is kind of commuting. And even more, if you look at it, looks almost like the Poisson kernel. And that's basically behind the idea, because if you now write actually the series here down, which I mentioned previously, you just have this term. And if you want to study invertibility, then the only term which really matters is this guy. And that leads to the introduction of the so-called S spectrum. So you take basically a bounded operator and you define the resolvent set as all the quaternions for which the second order operator is invertible in the bounded ones. And the spectrum, of course, just by taking the rest, which is not in the resolvent set. And since this one is the essential one, we call it a pseudo-resolvent operator. And basically the question is how to study that operator. There's one thing which is a problem with that operator, and that's basically, you can see it already up here. If you take only this part, it's not, there's no notion of analyticity connected this, or no direct function theory involved in this. If you have to multiply it with this guy, and then you would have something, and then you could basically say, okay, I can introduce a notion of holomorphic or hyperholomorphic or things like that. The simplest idea would be simply saying, okay, S is a quaternion here, but what I could do is just, I take any kind of slice for a fixed direction. And if I do that, then the function is holomorphic. So I could, in the simplest case, simply start, okay, I want just that my function is holomorphic in each cut. So it's not that quite simple because, well, you can do that and you can introduce that notion. But there's one thing. You can, of course, multiply from one side and from the other side. This guy here on top is basically what we had before. So this one would be, in some sense, holomorphic or hyperholomorphic, or slice hyperholomorphic as it's called, from the right. So the left resolvent would be hyperholomorphic from the right. The right resolvent operator would be hyperholomorphic from the left. But turns out you need both of them. You cannot just limit yourself things. So you can use that one basically as your Cauchy kernel, both of them. Each one gives you basically a theory, but you need both of them. The easiest way to see that one is if you actually just look at the resolvent equation. I mean, the standard resolvent equation in functional analysis is rather simple. You basically, if everything would be here commuting, you would just take that term in evidence, cancel out the things put to the other side, and you basically get the standard thing like that the resolvent in S minus the resolvent in Q is S minus Q times the product of the resolvents. That would be just the standard one. Here, we need both of them, the right and the left resolvent need to both of them. That's also the problem when it comes to the function theory involved. You need both. You need left holomorphic and right holomorphicity at the same time. You cannot just say, I just stick to one of them. You need to combine it. So, but we want to use that one to study actually triangularizations. What do I actually mean with that one in our case? Well, if you just go for matrices of finite rank operators, you basically, that's basically linear algebra first semester. T, if I go for T here, then I just have the decomposition. Any operator I can always in the diagonal, the nilpotent part. Basically, if the nilpotent part is 0, then it's diagonalizable, etc. All that thing. The point now is if you just let it act on any orthonormal basis, so you just take any orthonormal basis, let T act on the orthonormal basis, you have that expansion. You can take the orthogonal projector onto the subspace generated by each of the elements, and you obviously have this guy. That's pretty much standard, and you can introduce the projectors or a sequence of projectors P0 until Pk, where you basically sum them up. And if you do that one, that's basically in the Quaternions or Clifford the same as in the standard one, because it just really works only with projectors. You basically have that decomposition. T you can write like this, and okay, you can split it. And then this one is a diagonal part, this one is a non-diagonal part, and you have the projections to all the eigenspaces of the operator or of the matrix. That formula usually is not very well liked when you talk with persons working in linear algebra, because they usually don't like it, kind of trivializes linear algebra. But in any case, that is basically the formula which interests us, because we actually would like to know how that one works in the general case. So how that one works if our operator T is, let's say, non-self-adjoint and unbounded. So the big question we want to discuss is, how does it work in the general case for us? Well, first of all, I have to, well, probably you all knowing that one, but I just want to make it sure that that one has it. So I will actually just talk about eigenchains of my operator. So I take a set of autoprojectors and call that one the chain. If I take any pair, the image of one is inside the next one. Doesn't matter right now here the order. Basically, the eigenspace is inside the next one, which is basically exactly what I had before in my example. I call it bordered if 0 or I belongs to the whole thing. So either I get the whole thing or I start with nothing. And the important part is the gaps. Let's say I call P a pair P plus P minus, or a pair of two operators P1, P2, a gap, if basically all other elements in that set are basically either contained P plus or are contained in P minus. So basically in the previous element here, basically all these P would actually do that one here, but this is a standard case, so there's nothing to be said about that one here. So they're all actually having this part here. Now, I also want to be a maximal chain, so I don't want to have that one possible to enlarge. And I consider as an eigenchain if basically all the spaces generated by my P's are eigenspaces or invariant spaces under that operator, which is basically what that one is saying, nothing more. So I just want to have eigenspaces of the operator. So then I can use these eigenchains. And of course, I also need to discuss what a Volterra operator is. In here, there's one thing you have to keep in mind. We are the Quaternions. So strictly speaking, what we are working with is not standard linear spaces. I have to use modules. That means basically I can actually define multiplication on the right or multiplication on the left. Here, to make it easier for me, I just consider multiplication on the right and on the left, and I require, it's a Hilbert module, so it's closed with respect to sesquilinear form. And T can be a right or left linear operator. The only important thing is that the spectrum only contains 0. So it's a Volterra operator. In particular, as a Volterra operator, it's quasi-nilpotent. Does not need to be in general nilpotent, but it's quasi-nilpotent. So, and one characterization, which is the same thing in the case of, in the Quaternionic or Clifford case, the same thing as in the classic case is that's only based on the property of the eigenspaces, that if you have a maximal eigenchain and on every gap, if you put that one together, that thing must be 0. Basically, if you look at the previous one in the, well, look at the part of matrices, it's simple. That would be basically the diagonal part, which should be 0. So on that part, that's basically what we want to have with the Volterra operator. Now, we need a little bit more. We need integration over a quaternionic chain since we are going continual. So I can define the integral over the chain in the usual way. Usual way basically means via Riemann sums or Riemann-Stieltjes sums. So you basically take the differences, etc., and then you take the limits in all the things, and you take f inside each of them, just as basically that part. Here it's not really actually important if you are, for this one it's not really important that it is actually quaternionic. The functions are quaternionic or not, or Clifford, etc. That doesn't matter here. That's really just the standard definition. One thing which comes out also here is basically a necessary condition for convergence is that on every gap, every jump basically you have here, that difference must be 0. Otherwise it's not going to converge. One trick one can use, which is basically if you take the adjoint operator and apply the and look for the EJ, EK, so that if you take the projectors from both sides, then you see basically that this is, if you conjugate the whole thing, is going to be basically the same thing as if I would take this spot, only with that operator T, only with the projectors on opposite sides and the conjugation of that one. And that means basically that's really a simple calculation. I would actually just pick up this one, and I can write my operator T, any kind of operator T here, by this part, well, bounded or unbounded, by this imaginary part in P here. There's one thing why that one works in the Quaternions, which one should not forget. It works because actually the Quaternions or the Clifford algebra, just like the complex numbers, are a Z2 graded algebra. So if you have a more general algebra, for instance Z3 graded or so, you would have to modify this one, basically going for another character or another representation here for the things. But I'm not going to do it inside. I just want to mention it, that you basically, in this case, you have as imaginary part this part, but that's really actually coming from the grading of the algebra. So if there's another grading, you actually modify that operator. So now, what we're actually now interested in is so-called pre-triangular operators. So I consider an operator. I take it maximal resolution of the identity. So that thing should have a maximal eigenchain. And that thing should be possible to decompose into a D, a normal operator, and a Volterra operator. The important thing is that basically the eigenspaces, the invariant eigenspaces of T are also the invariant eigenspaces of D and V. That's basically what I wrote here. So that should not be changed there. And D is then basically the diagonal part, and V basically represents the nilpotent part. Well, it's actually in general quasi-nilpotent, but anyway, from the finite rank case, D would be the diagonal part, V puts the other part, well, V would be the nilpotent part. So, and that's basically the operators I'm now interested and which we want to study. Now, if you do that one, some properties are essential for us. The first thing which is essential is in the Quaternionic case, if I have two operators and they should have the same maximal eigenchain. So I don't want the eigenspaces the invariant eigens should be the same ones. Then one of them is a Volterra operator. Then the composition, it doesn't matter if you compose with V from the right or the left, are Volterra operators with the same eigenchain. So I can also apply V to T and I still have that one. And another one, which is also essential for the rest, is that if I have a p-triangle operator with Volterra part and diagonal part, or nilpotent diagonal parts of T, then for any point S in the resolvent set, I want that I also have that the operators V applied to the to the pseudo-resolvent are again Volterra operators, and all these operators have the same maximal eigenchain. This is essential for all what we are working afterwards. If that one is, and this is basically a kind of key lemma. It's not difficult to prove, but it's necessary for all the things to work. Otherwise, you actually just have to jump between spaces. It doesn't work. So another thing which is also then coming out, which is to be expected, if this S spectrum makes any kind of sense, then you want to have that the spectrum basically of the S spectrum of the operator is the same as the spectrum of the diagonal part. I mean, for V, the spectrum should be 0, so it should be encoded completely in the diagonal part. That's basically what one would like to have here. Now, to continue, I have now another problem which appears in the noncommutative case or in the Clifford case, same as in the Quaternionic case, and that's the question of trace of an operator. Trace class, or in particular Schatten-von Neumann class. The problem is that's again the rotation or the effect that actually as eigenvalues you have spheres, is basically that if you define the trace operator in the usual way, so just take orthonormal basis, A applied to the orthonormal basis, inner product with the basis, and sum the whole thing up. If you do that one, you actually quite fast realize that thing depends on the choice of the basis. So one thing you actually basically automatically think from the classic one, that the trace operator should not depend on the choice of basis, is not happening in the Quaternions. It's not happening in Clifford-algebra, in the Clifford-algebra case. The reason is basically we have equivalence classes, and of course I can change the class. I can always rotate around, and that's basically this thing. So you could actually restrict yourself to one slice or to one direction, and then of course you are in kind of semi-complex case, but you have to be careful. You cannot simply just restrict to one and use that one and then simply say and another one is the same. It's not really true. So you'd still have the multiplication and everything between different slices. So one thing which does not work is just saying, okay, I just restrict myself to one slice, work everything out, and then rotate it around. That's not working because you can have basically the part in two slices. So which basically means that I have to be careful with the trace operator. It's not independent, so I cannot really use it by that. On the other hand, T star T, I can still consider. And that obviously has a real spectrum, positive, so I can take the square root, so I can still take my eigenvalues, my singular values. That works. So, which means I can introduce my own or equivalence of the Schatten-von Neumann classes or the Schatten classes. The only problem is it's not only depending on P, like in the classic ones, but it also depends on J. I mean, the definition is essentially the same with that additional contact that it depends on J. You take a bounded unitary anti-self-adjoint operator, and my operator, the commutator with that one has to be 0, then it's in that class. It looks strange, that condition, a priori, but keep in mind that we have equivalence classes from eigenvalues, and strictly speaking, what that J is actually doing is you choose the direction. That's essentially what that J is doing. I mean, that J basically acts like imaginary object or imaginary unit, or how you want to say it. You basically just fix the direction with that one. It does not have any influence on the norm itself. So that one is basically just the definition, like in the classic case, you just take these ones. But you have to be careful, you always have to choose one direction, and then. In fact, you can choose not just one, there's always more than one, of course, because you can always turn around, but it just depends still on that J. Now, if I do that, then I can now look for the spectral decomposition. I can take basically T, for instance, at the first moment as a bounded operator. And of course, I take my imaginary part. Well, you can call it also something else. I just call it imaginary part because in the complex case, it would be imaginary part. But you can this one, and you can choose it. And let's assume that that one is in one of these Schatten JP classes, P between 1 and infinity. Then what you can prove is that there exists a maximal orthogonal resolution of the identity and a spectral function H, and you can basically decompose it like this, where H is basically my non-decreasing positive function. So basically, if you look at the standard classic case, or finite would be just jumping, but here you basically have this part, and you basically have that. And the second part basically corresponds to the part of the, well, basically this one corresponds to the diagonal part, and this one would be the Volterra part. In that case, T is here between A and B. In the unbounded case, you make the usual the usual condition that the domain of T and this adjoint has to be the same. And then you have to integrate from minus infinity and plus infinity. The proofs are a little bit long here. It actually uses really the fact, well, here it really comes into play function theory. If you want to prove it, basically what you are looking here is really at modules of slice hypervolomorphic functions. And it's essentially adaptations of the proofs of de Branges, like he did it for the complex case, with the substitutions of the things. Although there's one thing you have to be careful always with de Branges. His proofs are full of ideas, really, and they usually work out, but be careful with the proofs itself. They usually contain errors. I mean, that's a little bit the part. I would never use a proof of him which I didn't check myself. So never really, I mean, they should be careful. On the other hand, they're full of ideas and full of things, so they're always good to check, but never actually assume that, well, always check for errors in his proofs. He is sometimes rather loose. But still, that one is. So, as I said, I'm not going here, I don't have the time for actually explaining here that part because it's a little bit longer, but you can basically think it's essentially function. It's also essentially function theoretical approach here. You basically look at spaces and put the whole thing up, etc., and study that function H here as a spectral function there, and use basically the left and the right resolvent as corresponding Cauchy kernels. So if you have that one, then one thing you can do now is you can make an estimate for the pseudo-resolvent. For that one, you can basically take one restriction that you take V to belonging to a symmetrically normed ideal. For instance, one of these, well, here's basically afterwards these, of course, these Schatten P classes we have here. There is one thing you have to be careful here when you do that one. You choose then a sequence of points and you will such that you can estimate the norms of the powers of Vk by theta and the norm K norm in the ideal. Usually later on, what one actually uses is theta K, of course. The standard trick is you take it as a constant divided by the square root of the factorial of K. One thing you have to be careful here is the decomposition of that one, since the second order operator is not as simple as in the case of in the classic case. If you take the classic case resolvent of T, then immediately you just put the resolvent of D out, and the rest of the operator would be just one plus or minus the resolvent of D, inverse of the resolvent of D applied to your Volterra operator. Here, or the nilpotent part, here's a little bit more general. So you basically have to use that decomposition completely. And what you actually do then is basically look at this operator, show that it is nilpotent or Volterra, as it's actually a nilpotent operator. Then, of course, for each S for each S in the resolvent set, it has a nilpotency index, and then you basically cut it down to that part and estimate the distance. Keep in mind the distance here between the spectrum and S is in fact not the distance between S, but actually the equivalence class. So basically all the S's, the entire sphere which is generated by S, and not just the point to the powers in that part. So that's the first estimate you can use. Then you can modify that estimate slightly, basically taking this part, making the same with theta k with 1 over modulus of k factorial and estimating it. And if you do that one, then there is one step where you can now use a small trick. Well, I just put it here. Don't know how familiar persons are with it. I mean, it's I would say not a kind of obvious trick, but semi-obvious. If one knows it, it's always easy. So you basically take the series of square root of the exponential. The C case, your constants there as a fixed constant, and then you can split it, and you basically can say this one is always less than this term here, where you have exponential of C x squared over 2. And if you use that one, then you get, with some other estimates, get this estimation here, where N2P is basically the norm in the Schatten class. Here, you just choose J, and of course the norm does depend on J, so you can basically do that one independent of what J you have. And here you have the exponential. And since we have that part,
I'm sorry for interrupting,
yes,
but I think we should
that's basically the last slide.
Yes,
if you give me.
Thanks. Yeah, of course.
And if you do that one, then you can basically get the main theorem, or the main thing, that you can actually also in the quaternionic setting take a generally unbounded quasi-emission operator T with the usual conditions. And the only thing you want is that the imaginary part, well, is a Hilbert-Schmidt operator, and then you can say it admits a triangular representation, and you even know that that entire term here basically is the same as the N2 norm of the Volterra operator. And if one wants now, I mean, one thing we can extend it to operators which, for f of that one, which is slice hyperholomorphic, or quasi-unitary operators, so operators which actually fulfill that one, can be extended. We didn't do it, but it can be relatively easy done. I mean, that's not really actually here anything where noncommutativity or anything comes really into play here. So, and yes, we are on the end. So thank you for your attention.
Thank you very much for this interesting talk. So are there any questions? And then I would like to ask you to keep them short, since we've already actually in the break.
I have one question.
Yes,
yep.
Please.
Just I want to know if in this version of the spectral theorem that you have for unbounded self-adjoint operators, you have one formula of the spectral resolution in terms of the operator, like in the usual sense that one can recover the spectral resolution using like the Laplace transfer of the heat kernel or
well, first of all, this one is here actually the decomposition. That's not the spectral theorem. That's just, this one here is the decomposition when you have a non-self-adjoint unbounded operator that you can split it if the imaginary part is off. The standard spectral theorem for normal self-adjoint normal operators or normal operator is basically saying that you can take your operator and then you can decompose it in, then there's an operator J, which is unitary but non-self-adjoint. You can write it A plus JB, where A is now really a self-adjoint operator and B is a kind of partial isometry, I would say, this part. The spectral resolution, you can get that for sure, but I would have to check. I don't know what how it actually would look like here in this case. That I would have to do, to check. That I cannot tell you right now, but that you get it, that is possible. But how it looks like right now, I have no idea. I would have to check that.
Thank you very much.
So.
Okay, are there any other questions? I mean, I've got one, but I'm gonna ask you later, maybe in private during the break. So if not, then thanks again to both speakers. And yeah, there's a 20 minutes break now, roughly. So let's maybe stick to our schedule and reconvene at 3:40 Brussels time. Thank you.